Okay, so I have to, give an introduce first, and I should switch back to Chinese now.
Okay, fine.
各位同学、老师，大家上午好，欢迎大家参加我们这个强国论坛第19期。那么本期的强国论坛也邀请了加拿大拉瓦尔大学矿床学报告。那么前2期，我们的来自拉瓦尔大学的George 和 Crystal 2位教授，就造山型金矿分别做了非常精彩的报告。那么这一期也是大家非常期待的关于斑岩矿床的一期报告。那么首先请允许我介绍一下本期的讲座嘉宾。本期的讲座嘉宾Bertrand Rottier 教授是2019年任职于加拿大拉瓦尔大学。那么教授他现在的研究方向主要是为岩浆和热液矿床的成因机制以及物理化学演化的过程。那么目前研究的工作主要涉及加拿大境内的斑岩型铜金木矿床和与岩浆相关的稀土矿床等多种类型矿床。那么教授他做了非常多杰出的研究工作，也取得了很多的荣誉，其中有他在MD 国际矿床学权威期刊上发表的论文，曾经也获得了2019年国际矿床地质协会年度最佳论文奖。同时他也于今年获得另外一个非常重要的国际协会，也就是国际经济地质学家协会设立的今年科学家奖。那么今天教授将会为我们带来精彩的报告的题目是Chemical and Physical Processes Controlling Metal Endowment of Copper Gold Porphyry Systems。接下来就有请教授为我们做报告。谢谢。Please, Professor.
Hello, everybody. So my name is Bertrand Rottier. I am a faculty at Laval University since 5 years. And today I will give you a presentation on the chemical and physical processes controlling metal endowment of copper-gold porphyry system. So today I will try to focus on the magmatic story. I will try to do it in 30 minutes more or less. And this work has been mostly done with Professor Cécile Michaud, which is now a faculty at the ETH Zurich. So, do not. Okay. Do you see the slide moving or not?
No, just the first page.
Okay, something wrong. I will stop to share. We'll share again. Okay. So let's see what's happened. Okay. We'll start again soon. Okay. Let's see. Okay. Now it's working?
Yes.
Okay, sorry for that. So it's done in collaboration with Professor Cécile Michaud, which is at the ETH Zurich. So I think most of you know that, but it's always good to remind that is porphyry copper gold deposits are very important. Why? Is because they represent 80% of the world copper production and almost up to 20% of the world gold production. So it's very important deposit. So if we look at the map of porphyry copper deposit around the world, there is something which is very clear, is most of them are present in current subduction zones, like the Andes with giant deposit, for example, in Chile with Chuquicamata, El Teniente, Rio Blanco, Los Bronces, and we have also porphyry deposit along paleo subduction zone, like the one in Tibet. So why subduction is very important is because it's an area where we have the creation of calcareous magma. We create this magma basically by having the subduction of the oceanic crust and the oceanic lithosphere into the asthenosphere. During the sinking of the crust, we will have the dehydration of the crust that will liberate volatile in the mantle corner flow, and that is it's the first step basically to create our primitive calc-alkaline basalt, which will be at the that will form late in the evolution of the system, our upper crystal magma chamber, and then our porphyry copper dot system. So the porphyry copper dot system, or porphyry deposit, basically is a sweet result of magmatic and hydrothermal processes. And we can group them in 3 different steps. The first step, as I discussed earlier, is really the generation of the melt, in the asthenospheric mantle. Then basically we will have the polybaric melt evolution in the crust, starting from the lower crust up to the upper crust. And basically the last step is the magmatic free depth solution and the formation of the mineralization of the porphyry system, including porphyry copper gold deposit, skarn deposit, and epithermal deposit. So today I will mostly speak about the second step and the physical and chemical processes which are probably or not important during this step. What is important when we show this graph, and something that we should recognize, is all these processes are really relatively common in different subduction and post-subduction zones around the world. So we need to find what is basically the processes that lead to a formation of a porphyry copper dot system, which is not so common in a subduction zone. And the question that we have is basically why only some magmatic systems are mineralized. So that is the first question, but it's maybe not the most important. Maybe the most important is which factor controls the metal endowment of a porphyry copper dot deposit. Here on this graph, you have a compilation of the ore tonnage and the copper tonnage and the copper grade of porphyry deposits around the world. So you can see in terms of copper tonnage that we have a large variability of copper tonnage as function of the deposits. We have more than 5 orders of magnitude of size. And this means that we need to understand the factor that explains this large difference of metal endowment in porphyry copper dot system. Why we have some deposits which are relatively small, and why we have some deposits which are relatively big. And basically, if we are able to do that, I mean, it's like the holy grail. So basically, is what everybody wants to understand. So several processes have been proposed in the past, and we can group these processes more or less in 3 different categories. Some people have proposed that chemical processes are really the key processes to explain the metal endowment of porphyry copper dot system. They have proposed that, for example, that the metal content of the melt is very important, that the sulfur content of the melt is very important, that the chlorine content of the melt is very important. Oxygen fluidity is often proposed as a key factor. The occurrence, the absence, or the destabilization of magmatic sulfide is relatively often cited as a potential factor. And then we can also have physical processes. So we can have the flux of melt between the lower and the upper crystal magma chambers that can be relatively important. The efficient volume of melt and magma that will degas and degas volatiles that then will form our porphyry copper dot system. The thermal gradient of the crust basically seems to be important, and also maybe the shape of the magmatic chamber. There was also some other processes which have been proposed, like regional tectonic, local tectonics, and the nature of surrounding rock. So as you can see, a lot of different processes have been proposed, but the idea is to understand which one is the most important. Okay, this slide is a cartoon from Jeremy Richard in 2018, which have proposed that, for example, to form a porphyry deposit, we just need to have like a huge earthquake that will lead to a massive degassing of our upper crystal magma chamber that will liberate volatiles that will form porphyry deposit. So why not? I am not genesis model, but it's just to show you all the different kind of processes which have been proposed in the past. So it's not easy, to identify which of them is very important to control the metal endowment of porphyry copper system. So I will just go very fast because I am only 30 minutes on some ideas that we have about the chemical processes and the physical processes which can be key for the formation of porphyry copper system. And the idea is really to understand why we have this 5 order of magnitude in terms of size of porphyry copper system. So if we speak about the magmatic history, basically we can summarize the magmatic history of porphyry copper system in 2 different steps. The first one, we have the lower crystal magma chamber, where we will have a first accumulation of magma in the lower crust, and then we'll have an upper crystal magma chamber where the magma will degas and finally form a porphyry copper system. So what's happened in the lower crust? So basically what will happen in the lower crust, we have a transition from basalt, which around 10 weight% of magnesium oxide, to andesite with more or less than 6 weight% of magnesium oxide. So it's really like the first step of cooking of our magmatic system before and we know that based on the compilation of the geochemical composition of lava around the world, we see that during the step, we have a decrease of the copper content of the magma. So even if we will form a copper deposit at the end, during this step, the copper content of the magma decrease. So what's happened in the magma chamber in the lower crust? We know that to accumulate a large volume of magma in the lower crust, we need to have a system which is active during several million years before the formation of the deposit or even before the formation of a volcano. So why is more or less illustrated by these 2 cartoons is why so basically if you inject during a slow amount of time magma in the lower crust, basically this magma will freeze and basically will not able to have a volume, an efficient volume of magma that can differentiate and then be bring to the upper crust. So what we know about the magma chamber in the lower crust is this magmatic evolution in the lower crust will control the strontium-yttrium signature of the magmatic system. So we know that this strontium-yttrium signature is controlled by the fractionation of amphibole plus or minus garnet. So basically, as you can see here, based on these 2 graphs, this strontium-yttrium signature have often been associated with the fertility of porphyry system. So the work of Chiardia and Carici in 2017 and other people have shown that to acquire a good strontium-yttrium signature for porphyry copper system, so which is generally between 75 and 150, we need a long duration of the magmatic system in the lower crust and a relatively high pressure of magmatic differentiation. So it's more or less all the purple dots that you see on the graph here. But coming back to the decrease of copper, what's happened? Why we have a decrease of copper in our lower crustal magmatic chamber? Why is because probably we have sulfur saturation of our magmatic system. So sulfur content in a primitive basaltic melt is between 1000 and 3000 ppm. And sulfur is incompatible in the main silicate and oxide. So it means that sulfur is incompatible and sulfur concentration in the residual melt will increase. But the problem is it will increase up until the point that it will reach the sulfur saturation or sulfide saturation. So, and the sulfur solubility decrease with the evolution of the magmatic system. So the increasing of the ACO2 content of the magma and the cooling of the magma independently of the oxygen fluidity. So sulfur saturation cannot be avoided. But the question when we have sulfur saturation, we want to know if we have sulfide saturation or sulfate saturation. So is what we see on this graph from Baker and Moretti 2011, where we have the proportion of oxidized sulfur, so S6 plus, versus total sulfur as function of the oxygen fluidity of the magma. So we can see that we have a shift more or less at NNO -1 to +1, and this shift is first function of the magma composition. So this line is for basalt, and for example, this line is for urolite. And another work by Matchespin et al. 2016 have also shown that this shift between oxidized sulfur, so here, and reduced sulfur is also dependent of the pressure. So more you go at higher pressure, more the shift happens at a higher oxygen fluidity. So if we have sulfide saturation in the lower crust, which is probably happen because we are relatively at high pressure, so to avoid sulfide saturation, we need to be very, very oxidized, which is probably not the case. So if sulfide saturation happens, basically the chalcophile element like copper, gold will go in the formed sulfate phases. But sulfide saturation can be expressed in different terms. So we can have the exsolution of sulfide liquid. We can have the crystallization of monosulfide solid solution, MSS, and very rare and in very few cases, we can have the direct crystallization of intermediate solution, ESS. So why we care about sulfide liquid and MSS? That is not very important for copper because the coefficient of partition of sulfide liquid and silicate melt and the coefficient of partition of MSS and silicate melt for copper is more or less the same, is 1000, more or less. But for gold, it's a bit different because the coefficient of partition between sulfide liquid and melt is around 2000, and for MSS, it's only 300. So basically, the nature of the sulfate phase that will be saturated in our magmatic system will affect the copper and gold budget of our magmatic system, and mostly the gold budget. So here is an example. It's a very simple model where here you have the metal stored in sulfide. So basically, if it's not stored in sulfide, it's still to be in the silicate melt. And here you have the degree of crystallization of our magma. So if our system is saturated by sulfide liquid, basically most of the gold start soon after the start of sulfide saturation will be stored in the sulfide liquid. But if our system is saturated in MSS, we will have a delay and a large part of the gold will still to be in the silicate melt. So that is much more convenient if we want to form perfect copper gold system and not only perfect copper system. So what control basically the occurrence of sulfide liquid or MSS in a magmatic system? So to try to better understand that, we have done a compilation of different experiments which have been done by different people, mostly the group of Li and Odetat. So now Li is also a faculty in China. So they have done a lot of great work. And basically what we see is, we see that at relatively low temperature, like below 1050, most of the magmatic system will be saturated in MSS. And if we go above, we can have MSS plus sulfide liquid and then sulfide liquid. And if we go to higher pressure, basically this transition will shift to higher temperature. So if we consider like in a thick crust, most of the magmatic system, when they will reach sulfide saturation, will be mostly in the MSS field. So this means that we should not have, it's less common to have sulfide liquid saturation. But that is true for most of the arc magma, but we have also described that in other settings it can be different. So that is just an example of a paper of geology. We have shown that sulfide liquid can be important for intraplate alkaline magma, but it's another story. I will not speak of that today. So what is the take-home message here is magmatic sulfide saturation in the lower crust seems to happen and cannot be avoided. So, and that is very consistent with the geochemical data that we get from arc melt inclusion. So that is everything, all the gray shadows that you can see here in this figure. And here we have the calculated sulfide content at sulfide saturation, sulfur content at sulfide saturation for different composition, magmatic composition. So we can see that basically the sulfur content in the silicate melt inclusion start to be quite high in the most primitive magma, and then they follow more or less or are below the SCSS curve. If we look to the copper content of the magma, they also are decreasing, basically as you can see here, with the magmatic evolution, which is coherent with magmatic sulfide saturation in the lower crust. And is also consistent with observation in magmatic rock of MSS in a lot of different studies. I just put mine, but a lot of people have the. So sulfide saturation will have an effect. So we'll have an effect on the metal and sulfur content of the evolving melt, and also on the copper-gold ratio of the evolving melt. Everybody is agree with that. But it starts to be more debated about the true effect that they have on the copper endowment of a perfect copper-gold system. Some people think that they are very negative. You can see all the paper of Parker al, which are very fine. We have some things that they are positive. So it means that it's good to have sulfide saturation because generally we can remobilize them. So you have an example of the paper of Whitclifson 2012 and also of Chris Enrich 2022. And there is a lot of papers that propose that they have no effect on the fertility of magmatic system. So I am part of this school. Other Andreas Odetta, I think, is part of this school, and also other peoples. So the people that think that sulfide saturation have a negative effect generally argue that oxygen fugacity is really a key factor to form a large porphyry copper-gold system. Why? It's because if our magma is oxidized, basically your sulfur in your magmatic system will be dominated by oxidized sulfur, so S6+. And there will be not any more reduced sulfur in your magmatic system, so you cannot form magmatic sulfide. So to test that, before to test that, first we have the effect of pressure. So we know that if we go to the lower crust, we are at higher pressure. So this shift this oxygen fugacity need to be very high to avoid sulfide saturation. So in order to test this hypothesis, we have also did a large compilation of basically the oxygen fugacity of magmatic system associated with porphyry deposit. So as you can see, we have all this list of porphyry deposit. Here you have like the range of oxygen fugacity for classical magma, here for MORB. And what we have seen is, yes, some porphyry systems are relatively oxidized, like NNO plus 1.5, NNO plus 2, but a lot of them are close to NNO. So that means that oxygen fugacity seems to be not crucial for the formation of porphyry type, porphyry copper gold deposit. So yes, arc magma are relatively oxidized, but it's probably not the key to form a porphyry copper gold system. So some people propose that sulfide saturation can have a positive effect on the copper endowment of porphyry copper gold system. So if you are interested by that, I really suggest to you to read the paper of Enrich and Connolly. So the people that propose that magmatic sulfide have a positive effect propose that we have like the formation of a vapor magmatic sulfide component. So basically we will have vapor on our magmatic sulfide that will decrease the density of the magmatic sulfide, and then they will be able to float in the residual melt, and basically to be bring to the upper part of the system, and then to release their metals. So this model is very fine, but the only problem with this hypothesis, if we look to arc magma which are relatively fresh, we have no copper-rich rock which is observed. So it means that if that happens, normally we should find somewhere copper-rich magma. Okay, so the people that propose that there is no effect propose that magmatic sulfide saturation in the lower chamber cannot be avoided, which is fully consistent with the model and fully consistent with observation in magmatic rock. So it means that we can probably form porphyry copper gold deposit with magmatic rock which are not very rich in copper, like 20-40 ppm of copper is probably fully enough to form a large porphyry copper gold system. So the processes which happen in the lower crystal magma chamber are probably not the most important one to understand why we are this 5 order of magnitude of formation of this 5 order of magnitude of copper endowment in porphyry system. And what's happened is this deep magma reservoir act as a chemical filters which standardize the composition of the magma transmitted into the upper crust. But it's not fully true, because we know that there is one factor which is very important. We need to have a magmatic reservoir which is active for several million years in order to generate an important volume of intermediate melt that will be transferred to the upper crust. So what will happen after the formation of this large volume of magma in the lower crust? We'll have the upwelling of the magma in the upper crust at a plus or minus constant rate. Something that we think is this magma that rise to the upper crust should not reach volatile saturation. So they should stay undersaturated. Currently, this point is a bit debated, but let's say that normally it should not degas. So, and generally this volatile saturation, in order to be very effective, should happen in the upper crystal reservoir. So in the upper crystal reservoir, we'll have the differentiation of and cooling of the melt. So our residual melt will pass from andesitic to rhyolite. So during this evolution, basically we will have the accumulation of the volatile. And that is really the last step before the formation of a porphyry copper gold system. So what will happen? So basically, we did very simple experiment in 2017. Yeah, 17. Where we have taken just only one unit cell of magma. and then we leave this melt crystallizing. And then what happens is basically when your magma crystallize, you will have your volatile saturation. Your volatile saturation at the first point will not be liberated because basically we will just have some bubble of volatile that will be present in our magmatic system, but they will not be able to migrate. In order to migrate, we need to reach a certain threshold of volatile in our magmatic system, as illustrated here. And then the volatile will be able to tunnel between them and then to escape the system. After they have escaped the system, you can crystallize again, extract volatile again, and repeat the processes. So that is true only for one unit cell of magma. But if you consider a full magma chamber, all these exsolution steps happen at the same time in the same magma chamber. And the volatile basically will be merged. So here is a very nice model of Lamy-Chapuis 2020, where it illustrates basically the migration of the volatile during the concentric cooling of a magma chamber. So when you are too much crystalline, the volatile are locked and cannot be moved. And when you are a nice spot of crystallinity, basically your volatile can migrate inside the magma chamber and eventually be concentrated at only one place that will be able to be absorbed in the upper part of the system and basically will be concentrated in the porphyry plug and then to form the porphyry copper system. So we try to investigate the influence of the chemical factor in this lower crystal, in this upper crystal magmatic reservoir. We have done that by modeling the composition of the residual melt of the Epsom fluid and the crystallization of magmatic sulfide and sulfate. So we have done something which is very simple. Basically, we have considered a silicate melt. It crystallized a mineral. With this mineral, we have the partitioning of copper or not in this mineral. And then we have complexified the system a sulfide and then also adding a volatile. So we look to the equilibrium between all these different parts of the system. And then we also vary different parameters like oxygen fugacity, chlorine content, water content, and other one. So we start with a fixed amount of metal and sulfur in the magma because we think that is controlled by the deep crystal processes. So the variation of these different variables allow to study their impact on the fertility of the system. So I will just present you a few examples of what we have done. So that is a model of the composition of the Epsom volatile during the crystallization of the magmatic system. So what you have in it is the sulfur and salinity of the fluid, so sulfur in red and salinity in black. And here you have in blue the copper content of the Epsom volatile, the fluid. So, and we have done this model for two different oxygen fugacity, NNO plus 1.5 and NNO minus 0.5. So it's the two extremes. This one is fully anhydride saturated, and this one is fully sulfide saturated. So we have modeled these two extremes just to see basically their influences on the system. So basically what we see here is for sulfur content, when you have reduced, first our fluid start to be very rich in sulfur, is because we have the dissolution of the magmatic sulfide. When we are basically oxidized, we have less sulfur in our magmatic system because the coefficient of partition of sulfur between the silicate melt and the Epsom volatile is less important in the oxidized system. And when we start to be very evolved, we have very few sulfur in the volatile, is because we reach anhydride saturation. If we look at the copper content of the fluid for oxidized and reduced system, we see very few differences. apparently you have more copper in your volatile when you are relatively reduced and relatively oxidized, but the difference is not huge. Then I just want to show you the effect of chlorine. So we have modeled the effect of the initial content of chlorine in the magma on the copper content of the H-sol volatile. So first things, more we have chlorine in our magma, more the fluid that will be H-sol will be saline. So as you can see here, if we have 3000 ppm, with the composition of the fluid that will be H-sol correspond to this line. And at the end of the crystallization of our magmatic system, the salinity of the H-sol fluid will be around 7-8. And then here you have the copper content of the fluid. So we see that more we have chlorine in your magma, in your silicate melt, sorry, more we will have copper in our H-sol volatile. So it seems to be important. So it seems to be sweet to have high chlorine content. So here this is for oxidized system, this is for reduced system. As you can see, there is only very few difference. For reduced system, we are just a bit more copper in the magmatic system. But if we look carefully, I mean, chlorine content is fine in a way that it has an impact. If you have more chlorine in your silicate melt, you will have more copper in your H-sol volatile, but it's just one order of magnitude. So basically, all the tests that we have done on the chemical factor that can happen in the crystal magma chamber give only variation of size of deposit about one order of magnitude. So yes, chemical factor can be important, but apparently they are not enough to explain the 5 order of magnitude that we see in the copper endowment of porphyry system. So even if chemical processes seems to be important, it seems to be not the key to understand what control the metal endowment of porphyry copper gold system. So it's just a question, do we still need geochemists? Obviously, I am a geochemist, so I think yes, but let's see. So how we can explain this range? So I will just go very fast on the physical processes. I am not a physicist at all, so it will be very basic. So I will just try to give you some insight. So the first thing that we know about the physical processes is if you want a porphyry copper gold system, you need to focus your fluid. If you have passive degassing everywhere in above your magmatic chamber, basically you will form mineralization that will be very disseminated and very low grade, and it will not be possible to mine it. So you need to have all the fluid focused in your porphyry plug in order to form your large porphyry copper gold system. So a lot of work have been done in ETH on this topic, and notably experiment by Lamy-Chapuis in 2020. So what we see is when we have our pooling of your magmatic system and it's relatively long-lived, we can have like accumulation of the volatile and migration of the volatile in the relatively crystallized part of our magma chamber and focus it only at one point. I will not go to the physics which explains that. I really suggest you to read this paper. But if we want to summarize, something that we know is apparently size matter. If we summarize, if we do something very thematic, if you have in your upper crust a small magma reservoir, you will form a small porphyry copper deposit. But if you have a big magmatic reservoir, you will form a big porphyry copper deposit. Okay, but to have a large magmatic reservoir in your upper crust is not easy, because you want to have a big magmatic reservoir, but you really want to avoid eruption, because if you have eruption, basically you will drain the volatile out of your magma chamber, and you will not be able to form a porphyry copper deposit. So that is probably the most tricky part of the formation of porphyry copper deposit. So on this graph, you have theta 2, which is the ratio between the rate of relaxation of the crust and the injection rate of magma. And theta 1 is the rate of cooling of our upper crystal magmatic chamber and the rate of injection. So basically, if we have slow injection and rapid crystallization, we'll have eruption that will be triggered by the second boiling. If you have rapid injection and slow crystallization, we'll have also eruption, which will be triggered by mass injection. So basically, we need to be below this curve. And if we are below this curve, we will not have eruption, and it's mostly because we'll be in the viscous crust. So on this graph, so it's the same one, but we have shown the extrusive-intrusive ratio and in red, the volumetric growth rate. So here, the volumetric growth rate is how much your upper crystal magma chamber will rise and will become big. So if it becomes big, it's good because you will have a lot of volatile. So what we see here is we'll have like kind of a sweet spot for a relatively specific rate of injection in the magma and specific cooling of our upper crystal magma chamber. So this spot is relatively here, and this spot means that you will need to have like kind of an optimal like rate of injection of your magma in your upper crust to be able to form a large magmatic chamber. We know that already. Some work which have been done by Chiaradia and which is probably now published, is not submitted anymore. We know that because when we look to different porphyry copper systems, we know that the overall duration of the magmatic system has a kind of correlation between the tonnage and the metal endowment of porphyry copper system. So we know that we need a long time and a high volume of magma to form a large deposit. And here is basically we have tried to determine the volumetric intrusion rate, which is very tricky to determine for different porphyry copper gold system as function of the volume of magma. And the few data that we have suggests that most of the porphyry deposits have an intrusion rate which is more or less between 10,000 minus 3 and 10,000 minus 2 kilometers cubed by year. If we are injecting too fast, basically we'll have eruption, which is also bad for the formation of porphyry copper gold system. So if we want to conclude, so I think the future of the case for fertility in magmatic system is maybe not in the hand of geochemists. So magmatic reservoir in the lower crust basically act as a chemical filter. So the oxygen fugacity of magma do not affect the fertility of magmatic system in the lower and upper crust, and the volume of melt in the upper crystal magma chamber seems to be the most important factor. Okay. Thank you for your attention.
Thank you, Professor Bertrand。各位老师，然后大家看一下，有没有什么问题，咱们可以提出来，和我们的Beaudoin教授做一个讨论。
Hi, Bertrand. This is Cal. Can you hear me, Bertrand?
Not really well. Can you speak?
Sorry. Hi.
Hi, ciao.
Can you hear me now, Bertrand?
Yeah, it's better. Thank you.
Yeah, thanks for your nice talk, Bertrand. And also, it's nice to see you giving the talk to the Chinese audience. So here I have a couple of questions, but to give more time to other people, I just want to have ask two simple questions. And you show the solubility of MSS, and the sulfide liquid. I'm wondering how can you get that kind of solubility data, because for that kind of things, usually in the field or under the microscope, it's so difficult to observe that. So I'm wondering, how did you get that kind of solubility
This one?
data? No, the sulfide liquid and MSS.
So under the microscope, you mean? How we recognize if it's MSS or sulfide liquid?
Yeah.
So it's not easy. Mostly we use the chemical composition because MSS as sulfide liquid will be rounded. I think I have some slide. Yeah, I mean, maybe it's not the best, but it looks like that. In terms of, we find them in inclusion in different hosts, and basically, I mean, when you look under the microscope, even if you have a very copper-rich one, so a high concentration of sulfide of chalcopyrite, if you have a lot of chalcopyrite, you have probably sulfide liquid. But the inverse is not true. It means you can have a sulfide liquid which is not really copper-rich, so it will look like MSS. And MSS and sulfide liquid look like rounded. A lot of experiment has been done. It's not because it's rounded that it's sulfide liquid. It can be MSS. So basically then it's mostly the composition, because the coefficient of partition between MSS and sulfide liquid with the silicate melt are different. So based on the composition, you can more or less know which one is found.
Okay, thank you. Then I have another question about the fluid release process. You mentioned that during the crystallization of magma at a certain stage, then the fluids will be released. And I'm wondering, the fluid release process, it's kind of a stable, continuous process, or like at some stage it can be released very suddenly, like in El Tinite and Rio Blanco, Los Bonoses, like they have a huge amount of like hydrothermal pressure. So I'm wondering, it's like very stable process or can be like very sudden release process?
Yeah, it's a very good question. I am not sure that I will be able to understand that. So what is clear is volatile. So there is a difference between fluid H solution and degazing. So fluid solution is when your magma start to be saturated in volatile. So it doesn't mean that the volatile leaves the system. They can stay in the system. So degazing is when your volatile will leave the system. And to have an efficient degazing, different process can happen. So you can have like your accumulation, and is what most of the people think is the most important, is to have like volatile saturation like here. So it's not degassing because the volatile seem to be in the magmatic system. And you can have a perfect kind of sweet spot where you can have the liberation of volatile just really quick and only at one place. And that will be your degassing. And then in the Rio Blanco, Los Bonoses and other deposits, we can have different events of degassing, not only one. It's totally possible. So it's basically linked to the magmatic history of the system. I don't know if I answer your question.
Yeah, I get it. Yeah, thank you very much. Yeah, although I have more questions, but I hope to exchange with you through emails. Thank you.
No problem.
Professor, we have a question from who leaves a audience leaves a comment. He said that thank you very much for your speech, and I'm just wondering if hydrothermal precipitation process is also a critical factor influencing the endowment.
I think yes. Yeah, sure. It has an effect. And I didn't discuss it during the presentation. And yes, it probably has an effect. Now, we think that it's probably also kind of an order of magnitude. Just hydrothermal processes by themselves is probably not able to control like the 5 order of magnitude that we see for copper endowment in porphyry system. I'd have maybe yes, I think no, but is we need to stop to share again and share it again. Something that can be a kind of an indication of that is the lack of correlation between the copper grade and the copper tonnage. Because if hydrothermal processes like very efficient precipitation of copper was very important for that, we should expect to have like high copper grade system which are the more endowed in copper, but it's not really the case. So it means probably that we need a large volume of fluid to form big copper deposit. But I am not totally against the fact that hydrothermal processes have a role in the copper endowment of porphyry copper gold system. But it's another talk.
Thanks. But I do have a question. I'm curious about that you mentioned about how to control the fertility. I know you had the best paper, award-winning best paper, 2018, but the best award-winning paper before yours was about the depth, the controlling, the ratio of gold and copper. So there's a recent debate or research is going on with regard on this matter for the importance or how do you think about that?
I fully agree with the work. I fully agree with the work of Murakami. So basically, so something that we know about the hydrothermal step, I need to find a slide. Where can I have? No, I don't have the slide. So basically, if you have shallow degassing, it's very bad for copper. So basically, if your stock is very shallow in the crust, you will have very few precipitation of copper in the crust, and you will have a relatively small porphyry copper deposit. Why? We think it's because the thermal gradient of the crust will be too fast. So it means that you will have your plug and the surface will be very close. So it means the gradient of temperature between the top of your porphyry system and the surface will be too sharp. So basically the fluid will not have the time to cool and will not have the time to precipitate copper. But that is a very specific situation of shallow porphyry copper system, which is not very common. We have some example in the Maricunga belt, some example also, I think there is one paper in Mineral Deposits which have just been published on that in Argentina, if I think well. But if we look to the large quantity, to the majority of porphyry copper gold system, basically, I mean, the plug is in place around 4, 5, 3 kilometers, so which is fully enough to have the cooling of the hydrothermal fluid and the precipitation of copper sulfide.
Okay, thanks. 各位老师yeah. 各位老师，大家看看还有什么问题没有？如果大家有感兴趣的，也可以在评论区里面留言。Okay, so as I think that that will be all. So yeah, so I want to thank our guest for today, Bertrand Rottier professor. Thank you again, and
thank you
for your excellent lecture. And yeah, and I introduced. By the way, I forgot. Professor.
Sorry, I lost you.
Can you hear me?
No.
Oh, can you hear me now?
Yes.
Sorry, the internet is not very stable right now. So I'm very happy to tell you that we have over 2,000 people participating online.
Okay, great. I hope I was not too bad.
Yeah. And this, that is great. And back from sure. So probably you would double the number.
Okay.
Yeah. And because this is a great topic, and it's a very hot research topic with regard to porphyry system. Hopefully we will have some cooperation in the future.
Great.
Okay. And 各位老师，各位同学，那大家好。那么再次感谢。首先我们要再次感谢Bertrand教授为大家做了这样一场非常精彩的这个报告。然后我们也非常感谢整个我们拉瓦尔大学矿床学研究团队，这次带来的3场非常精彩的报告。那么也非常感谢大家也参加了我们这一期的强国论坛。那么同时也希望通过我们和国际矿床学研究团队的这样的交流，能对国内的研究也为国内的各位学者能有所启示。那么我们的研究成果也能够为支撑我们的新一轮找矿战略突破行动发挥的有效的助力。那么接下来我们也将继续邀请国内外优秀的学者为大家分享精彩的报告。那么今天的报告就到此结束，再次感谢大家。Merci beaucoup, Bertrand.
Merci beaucoup.
Yeah, thank you very much. By the way, I forgot to ask you about this. Do you mind if we record the lecture?
No, it's fine.
Okay, thank you very much. And that will be all. And thanks. Have a good night.
You too.
Okay, bonsoir.
Bonsoir.
Oui. Bye bye.